how we can use this information to help us actually sketch the graph of a function. And this first one I know has come up in class before, but we know that if we have a function that's continuous on an interval, so notice that it's continuous and it's differentiable at all of the interior points. If the first derivative is greater than 0 at all of those points in the interval, then the function is increasing on the interval. So if I sketch a picture here, like you'll see, hopefully you'll realize what that's really saying. Note if I just ask you to come up and point out where that function is increasing, I think most of you could point to the right interval for me. So it looks like this function is increasing like from here, right? And then over here, that function is increasing again. It's going uphill from right to left. And notice that at those points, if we look at the slopes of the tangent lines, do you see the slopes of the tangent lines there are positive? So that is a way that we can tell where our function is increasing. A function is increasing whenever the first derivative is positive. If the first derivative is negative, that means that our function will be decreasing. And I hope that you see why that's true by looking at this graph. So notice that this one is decreasing here. And if I am anywhere in that interval and I draw a tangent line, notice that the slopes of those tangent lines would be negative. So any questions or comments about that before we go on? Okay, so let's see if we can use it. So here is a function, and we are supposed to find the intervals where the function is increasing or decreasing. Big word of caution here, you should not be using a graphing calculator or any type of graphing program to do any of these problems, right? You shouldn't even pick it up because you don't need that anymore to decide where a function is increasing or decreasing. We used that to approximate the values when we're in college algebra because we didn't know anything about a derivative, right? Whenever you're asked to find where a function is increasing or decreasing, you should know that you need to find the first derivative. That's what tells you whether the function is increasing or decreasing. So that's how we're going to start. We're going to find the derivative. And so I need to use, I could actually distribute and not use the product rule, but I'm going to go ahead and use the product rule. So I have the first one times the derivative of the second plus the second one times the derivative of the first. Help me out. What's the derivative of x to the 2/3? What's the derivative of x to the 2/3? Yeah, drop the exponent down. We're just using the power rule, right? Good job. So it looks like that. And so in the last chapter, again, when we were just finding the derivatives, we often just stopped there. But now we are going to have to use that function to do something. So we're going to have to simplify it. So I'm going to rewrite it. So if I have x to the 2/3 times x to the first, that would be x to the what power? What's x to the 2/3 times x to the first? What do we do with those exponents when we're multiplying? Yeah, that would be x to the 5/3. And over here, I have 2 times x squared minus 4 over 3 times x to the 1/3. And we are going to have to find out where that derivative is positive and negative. So that means that we need to find the places where the first derivative changes sign. And it can change sign when it's either equal to 0 or undefined. So in other words, we're going to have to find the critical points. All right, so notice that I am adding those together, so I just have one fraction to look at. So I need to multiply 2x to the 5/3 times 3x to the 1/3. 3 times 2 is 6. X to the 5/3 times x to the 1/3 is x to the 6/3. So that would be x squared. I'm going to distribute this 2. So finally, I get that I have on top 8x squared minus 8. On bottom, we have 3x to the 1/3. So we found the first derivative and we simplified it. So any questions about that before we go on? So the next thing we want to do is find where the derivative can change sign. And that function can change sign when it's either equal to 0 or undefined. So again, another way to say that is we need to find the critical points. And so we are going to find out where the derivative is equal to 0 and where the derivative is undefined. Okay, so this fraction is going to be equal to 0 when the top equals 0. And so if we solve that for x, we take the square root of both sides and we get plus or minus 1. Now remember, before we call those critical numbers, we have to make sure that they are in the domain of our function. So let's go back and look at our original function. And I'm going to jot down the domain because we want to make sure that we don't list anything as a critical number that's not in the domain of our function. So here's our function. So help me out there. Where is that function defined? In other words, is there any part of that function that would restrict the domain? Is there anything we cannot plug in for x? Good. The domain is all real numbers. Very good. If that had been a square root, we might have a problem, but notice we have a cube root there, not a square root. Okay, so that means that these values we found are in the domain of the function. So these are actually critical numbers. To find out where that derivative does not exist, we set the denominator equal to 0. And we know that will be equal to 0 whenever x is 0. And again, notice that that is in the domain of our function. So this time, all of these are critical numbers. And you had problems in section 4.1 where you had to find that. Okay, notice how this problem is different than the problems on 4.1. Since I said that, I want to make sure we talk about that. Notice on this one, we're finding out where this function is increasing or decreasing. We are not given a closed interval, so that means that we are talking about everywhere it's defined, everywhere on its domain. So after you find the critical numbers, okay, so what is happening here really is when you find where this derivative is greater than 0, so let's talk about that. So this is what this problem would have looked like in college algebra class. You wouldn't have had a derivative there, certainly, but it would have looked something like this. that problem, okay, even though you might not have known where it came from, that looks like what your problem would have looked like in college algebra class. You would have had some function that you're finding out where it's greater than 0 and less than 0. And so the steps when we did that in college algebra was to find out where it's equal to 0 and where it's undefined. Notice that's what we did right here. We just didn't call them critical points because we had no context of where that function came from. But then the next thing that we would always do is draw a number line. And we mark those points where that function could change sign. So in other words, on your number line, you are going to mark the critical points of this function. So in ours, we have a critical point at -1, at 0, and at 1. And notice I kind of made those big marks. Don't make those marks on your number line little tiny marks. And I know it may have been a while, so you may not remember, but just in case someone does, I want to give you a chance to help me out. Do you remember when you were solving those nonlinear inequalities in college algebra and you drew the number line, you marked the places where it was equal to 0 or undefined? Does anyone happen to remember what you did next? And it's okay if you don't, just let me know if you do or you do not, either way. Yeah, okay, so you don't quite remember. That's okay. That's why we're doing it now, right? The next thing that you do is test the intervals. So maybe we're saying the same thing, Jamie. You may just be saying it a different way. So, but I am going to pick a number in each one of those intervals. So I'm going to start over here. I'm just going to work left to right. I need to pick a number that's to the left of -1. Don't make your life hard, right? So pick something that comes out nice. You can pick -2 or maybe -10. Sometimes when you pick, like a multiple of 10, that makes the arithmetic easier. So do that. But remember that what we are doing is we are trying to decide if our derivative is positive or negative there. Okay. And so I'm going to erase this little part that I have here just to give me a little space up here to write. So we are going to plug that number into our derivative. So our derivative, I'm just recopying it from up above, was 8x squared minus 8 over 3x to the 1/3. I'm having a really long lag, so I know that you probably hate it when I have to do that, but I'm going to close it and reopen it. It'll save us time in the long run because it won't be quite so draggy. Okay, so back to here, right? All right, so we're going to recopy that derivative. 8x squared minus 8 over 3x to the 1/3. And honestly, I would go ahead and factor the top. Notice if I factor out an 8, that would be x plus 1 times x minus 1 on top. X to the 1/3 is the cube root of x. I'm just trying to write it in a form that will make it really easy for us to tell. Okay, so and remember we were plugging in -2. So we are going to plug -2 into our derivative. Now I'm going to help you to save yourself a lot of arithmetic, especially you can see we're going to have to plug in some fractions here. We really only care about whether that derivative is positive or negative, not the number itself. Now, -2, if we plug that in, that comes out really nice. So if you want to go ahead and do that, that's fine. But I am looking right here. If I plug in -2, notice I have 8, which is positive. If I plug in -2 into x plus 1, that's a -1. It's a negative number. right? -2 minus 1 is a negative number. You can write -3 if you want, but I want you to get the idea that I'm just checking the sign. What about the denominator? When we plug in -2, is the cube root of -2 positive or negative? Yeah, that's going to be negative. So notice if we were to simplify this fraction, I have a positive number on top divided by a negative number. So the answer there is going to be negative. So we are actually making a sign chart for the first derivative. And what I know is that if the derivative is negative, that means that my function is going to be decreasing. I'm a very visual person, so I like to draw those arrows on there to remind me that's what we really just found. The derivative is negative, so my function is decreasing on that interval. Okay, so we're going to do that same thing for every interval. So now I'm looking at this interval between -1 and 0. You need to pick some number in that interval. It doesn't matter what. I'm just going to pick -1/2. Now, if I actually needed that value, that might be a little bit of a pain. But remember, we only need to know if it's positive or negative. So go back to here. This is our derivative. 8 is positive, so that's fine. If I have -1/2 plus 1, well, we know that's positive, right? -1/2 plus 1 is positive. -1/2 minus 1, we know that's negative. And if I take the cube root of a negative number, that answer is negative. So if I simplify that fraction, I would get a positive answer. And if my derivative is positive, that means the original function is increasing. And so now I want to hear from you. Does that make sense what we did there before we keep going? Okay, because we need to do that for every interval. So we take the interval between 0 and 1, pick a number. So I would probably just pick 1/2. And remember that this sign chart is for the first derivative. So that's where I'm plugging it in. The first derivative is what tells us where it's increasing and decreasing. If we plug in 1/2, 1/2 plus 1 is positive. 1/2 minus 1 is negative. The cube root of 1/2 is positive. So when I work that out, I would get a negative answer, which means my function is decreasing. Then we have the interval to the right of 1. So again, I'm just going to pick 2. So on top, 2 plus 1 is positive, 2 minus 1 is positive, the cube root of 2 is positive. So that means the whole derivative will be positive. And if the derivative is positive, that means my function is increasing. Now, I still need to write the answer. I haven't done that yet. But any questions about that sign chart before we go on? All right, so the question said, find the intervals where the function is increasing and where it's decreasing. So this function is increasing everywhere the first derivative is 0. So now look at your sign chart, and we can see that it's increasing everywhere between -1 and 0. And it's also increasing for all of the values greater than 1. So it's increasing from -1 to 0, and then from 1 to infinity. Notice that it's not increasing at -1. That's why I have the open parentheses there. The endpoints are not included. The derivative is actually 0 at -1, not positive. The derivative has to be positive for the function to be increasing. But once you have your sign chart, now you can just write down the answers. So notice this function is decreasing everywhere to the left of -1. And then it's decreasing again between 0 and 1. So these are the places where that function is increasing and decreasing. So any questions at all about that before we go on? Okay, so I'm going to put a poll up here. So let me know how you're doing, because we are going to be building on this problem to do other things in this section. So I want to make sure you're okay before we just keep talking. Okay, so did everyone have time to respond to the poll? Thank you. All right, so let's go on then. So we know that a function is increasing when the derivative is positive, decreasing when the derivative is negative. And again, note the steps there. We took the derivative, simplified it, found the critical points, and then we marked the critical points on the number line. And by the way, this will come up, I think, today, but just in case it doesn't come up in one of our examples today, even if one of these points where the derivative was not defined, if those turned out to not actually be critical points, probably because they weren't in the domain of the function, even if they are not actually critical points, you still need to mark them on this number line, because those are the places where the derivative can change sign, where it could go from positive to negative. Okay, but now we're going to expand on that and use what we call the first derivative test. And so I know you can see the statement of the first derivative test there, but let's talk about what it means. First of all, your function has to be continuous on your interval. Notice that interval contains a critical point. All right, so if we have a critical point and our function is differentiable on every point in the open interval except maybe at the critical point itself, meaning that it could be a place there where you had a sharp point or something funny may happen right at that point. But other than that point, our function was differentiable. Okay, if your first derivative changes sign from positive to negative. Okay, so think about what that means. If your function, notice it's the derivative. If the derivative changes sign, so your derivative is positive, so notice if it's positive, that means your function is increasing, right? But then if your function is increasing, but then your function becomes negative, which means it starts to decrease. So if your derivative changes sign from positive to negative, notice that that would be a maximum point. And notice it says F is a local maximum. It may not be the very highest point on the graph, but it's a place where your graph will peak. Also, notice it could change sign from positive to negative as X increases through C. So that means as the X gets bigger, and that's the way that I drew it, but I should have actually said it that way. If your derivative goes from negative to positive, so that means it was decreasing, and then it started increasing, notice you would have a local minimum at that point. Just because your derivative is 0 or undefined does not necessarily mean that you have a max or a min. You can have a horizontal tangent line, so it could have looked like this. I'm trying to exaggerate it. There can be a place where you have a horizontal tangent line, but notice it's neither a max nor a min. There could be a place where you have a vertical tangent line. That would happen in like y equals the cube root of x squared. Okay, but it's not a max or a min. But if it as being the first derivative, if the first derivative does change sign, that means that you would have a relative max or min. That's what we call the first derivative test. So any questions about that? Okay, so now we're going to build on that problem we did earlier. Notice this is the same function that we had up above, right? That's the same function that we had up above, x to the 2/3 times x squared minus 4. We already found out where that function was increasing and decreasing, so I'm just pasting that. This is the work that we did earlier, okay? But now, instead of just finding out where it's increasing and decreasing, the problem wants us to find the relative or local extrema. That means that we want to find the relative maximum and minimum points. Okay, so first let's find the relative maxima if we have them. So maxima is the plural of maximum, so we may have more than one. We may only have one. But if you have drawn the arrows on your graph, like I did up above, it makes it a lot easier to pick out those maximum and minimum points. At least I hope you think it does. It definitely makes it easier for me, because notice what happens. We're saying our function goes down and then back up. And then notice it goes down and then back up. So do you see it would have that kind of shape? I'm just following those arrows I drew on my graph. But really, that's what the first derivative test says, that if your function, the derivative of your function goes from positive to negative, notice right there, that means we would have a relative maximum at x equals 0, which means if we want to find the relative maximum point, and so I'm gonna word it both ways here, because no matter how they ask you in my math lab, I want you to be able to get it. I only have one of them, so I'm gonna write it like this. I have a relative maximum of something at the point x equals 0. How do I find out what that relative maximum actually is? We did that same thing in section 4.1, only in 4.1 we had an absolute maximum. But notice now we're just finding a relative maximum. But that maximum is actually the y coordinate. So what do I have to do to get the y coordinate if I know x is 0? Yeah, plug it in. Exactly, Jamie. Where do I plug it in? I plug it into which function? Notice we have a derivative up there and we have our original function f. Which one do we use when we want to find the y coordinate? Yeah, the original function. So remember, anytime you want to know where your function is increasing or decreasing, that's the first derivative. We get critical points from the first derivative. But anytime we want to know the y coordinate of a point, we always go back to the original function. So notice if I plug 0 into that function, I would get 0. So our relative or local maximum point, the point on the curve, would be 0, 0. So if it asks you for the maximum value, that's the y coordinate. If it asks for the point, make sure you give it as an ordered pair. Okay, so now let's see if we have any local minimum points. And I think you can see that we do, right? So we are going to have local min where? Can you tell me where they will occur? Good, at -1 and 1. So notice I'm writing them as points this time. I know I have 2 of them. They occur at x equals -1 and x equals 1. And I can tell that by looking at my sign chart, but notice we're using the first derivative test when we do that. The first derivative test says if the derivative is negative and then goes to positive, that is a local min. To find the y coordinates, I go back to my function And notice if I plug in -1, I would have the cube root of -1 squared times -1 squared minus 4. The cube root of 1 is 1. So I have 1 times -3. And notice I'm going to get the same answer if I plug in +1 this time. So these are the local minimum points. This is the local maximum point. And again, when we used this sign chart to pick out the max or min, that's when we used the first derivative test. When you work that problem for me on the quiz and the test, and definitely every time you're working a homework problem, you should do this as well. You need to make sure that you're showing your steps, show where you found that derivative, show how you found the critical points, just like we did earlier. Make sure you show this sign chart. And even if you don't work it completely out, write this, at least this much down. Kind of what I have written there is the bare minimum that I would want to see on the test. But if you will write this down for me, if you make a careless mistake and miss a sign, I can tell you were trying to do it correctly, so I can give you partial credit. Because the sign is everything, right? So if you miss a sign, it's going to really throw off the rest of the problem. So please help me give you partial credit. Okay, so we are going to stop there and take a break. Let's let that sink in a little bit so you have time to figure out if there's something you want to ask about it. And we are going to come back and talk about some more graphs and finding maximum and minimum points. So take about 5 minutes and then we'll come back together. Sure, Bryce, go ahead.
Okay, so I was looking over my quiz